Hey, today's daily was sort of Subarray to remove to make array sorted. This is very like multiple solution problem. You can use whatever you want, either two pointers, binary search, monotonic stack, or like you can just see how many tags there in the problem. But the easiest of all is binary search. Now, why? Let me give you very smallest small example. If 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 I have to find a subarray. That should be my answer. Let's assume this is my array. So if I'm either I can remove this or I can remove this part or I can remove this part. So what I'm trying to say either we can remove from the beginning, from the middle and from the end. Such so that like if I'm removing this, then this array will be sorted. And if I'm removing this, then this and this array will be sorted. And if I'm removing this part, then my this array will be sorted. So there is like you have to find an end and the beginning on the array where you can just pick an element from here and here, such that if you join both of them, like if there's a connection between both of them, the monotonicity of this array, sorry, this array remains constant. So this is the intuition of the problem, that I have to find these points, or like whatever array is the case, you have to remove that. So taking into consideration with this uh, example, we can see I have one, two, three, 10, 4, 2, 3, and 5. So now we are increasing till this moment and increasing from here. But this element doesn't matches the monotonicity with this element, but this element does. Sorry, this also doesn't. Like these both element doesn't matches the monotonicity. But if we go from here to here, this does. From here to here, this does, and so on. So as we can see, our one end could be this. Like this is the left end where monotonicity is viable, and the right end is this. Like this is the array that holds the property that we're looking for. So this is our right end. But for every element, which is the most suitable point where I can just join these arrays. So I have to find the viable point for each point so that with whom I can match it, and the like monotonicity will be intact. So obviously the best choice is to go in this area. Like if I am searching for any element I will search in right to n in this array, in this segment of the array. So that's the like I can find my point. So if I have to find for one, I can just pick two. For one, two, three, four, 2, 3, 5 is my like desired can be desired array. So I have to remove this much, which is 1, 2, 3, 4. For 2, I can also pair with 3, 5. Now I have to remove 3. For 3, I have to pick 3, 5 first. 2 won't be viable. So here I have to also remove 3. That is 10, 4, and 2. Then I have to pick 10. If I'm picking 10, then I have to remove every one of them because this is not my viable point. So I can't pick anyone. I have to remove 4. So as you can see, these two choices are the best choice. And for searching, as as you might have understood till now, that if I'm picking element ARI, then I am searching the first element that is happening in the right segment of array, that is greater than equal to ARI, which is lower bound, which is basically lower bound of ARI. So let's implement that. It is quite easy of a problem, like not too much, but you just need to see that this thing, that you have to draw this diagram where what you have to remove and what you have to take. Or if you do this, the problem boils down to very easy binary search problem. So let's do that. First, I'll take a size of an array, a left pointer and a right pointer. This would be n minus 1. Now whenever left plus 1 is less than n, and AR of left is less than equal to AR of left plus 1, that is, I'm following the monotonicity here, like 1 2 3 something like that. Just give me the farthest point I can go, and if this farthest point is end point, that is 1 2 and 3, like in this such cases I have to remove nothing. Then it's greater than 0, so that I can access the, like, sitting on the first element I can access the last element, sorry, second. For I on sitting on the second element I can access the first element, and AR of right is greater than equal to AR of right minus 1. Do right minus minus. Great. Now my desired length would be the maximum. What can I have? The maximum can be have is minimum of n minus left plus 1 and right, cause right would be this and n minus left minus 1 would be this segment, like from here to, I'll have to pick a different, this segment, right would be this. So I will only be removing this segment. So this is my, like, kind of maximum point I can remove. I'll traverse from the beginning to the most point, like I'll traverse from this part. If this follows monotonicity, that for every I, just I have given example, this for every I, give me the like lower bound of in the rightmost segment. So j is equal to, right, so that I'm in the right one most, and my length is equal to minimum of length, sorry, j minus I minus 1. What happened there? Oh, yeah, it passes. Have a good day.